Now, like I already told you, as a technology is getting scaled down day by day, the smaller transistor length is getting into devices. So there is a higher sub-threshold current, or source to drain, we can say leakage current flows. And because of this, the low VT is obtained, VT roll-off is there. And also we are reducing the gate oxide thickness because scaling of the overall device is done. All the proportional length is reduced and width is reduced, thickness is reduced, okay, by a scaling factor, due to which the higher leakage current flows through the gate also, okay. So we can say as a technology node is reducing, there is an increase in VT. Earlier the VT was very less, but now the VT has increased, due to which the leakage current also increases. So this can be clearly understood from the graph. Now, properties of leakage current. Leakage current is also affected by the temperature. Okay, as we can see, the junction temperature is increasing, the leakage current is also increasing proportionally, and so the device temperature should also be controlled. The heat which is dissipated by the device should also be controlled. If it will cross the certain limit of the temperature, ultimately it will increase the leakage current of the device. Now, let us see the static component in the CMOS inverter. Let's take example, and we can see this is a PMOS and this is NMOS. When the input is 0, the PMOS is on and the NMOS is off. So some of the leakage currents flow through it also. And when the input switches from 0 to 1, the PMOS is now off and the NMOS transistor is now on. And at that time also certain leakage currents are present. So we can say leakage or the standby power or the static power is present in the on state as well as the off state of the device, that is the active phase or the standby phase. Now let us see and distinguish between all these types of leakage current. Now, from the figure, we can see this I1 is the reverse bias PN junction, which is present in both on and off of device. Then we have the subthreshold leakage current, which flows only when the device is in the off state. Then we have the gate leakage or the tunneling current, which is present when both on and off device. Then gate current due to hot carrier injection, I4, which is present again when the device is on or off. Then we have gate-induced drain leakage, that is the GIDL, that is present in the off device, and the channel punch through current, which is again present in the off device. Okay, so these are some of the leakage current which are flowing through the devices. Now, all these leakage currents are influenced by the threshold voltage, the channel dimensions, the surface doping profile, the drain source junction depth, gate oxide thickness, and the VDD of the device. So we will discuss one by one all these all these current components: I1, I2, I3, I4, and I6. Okay. But one thing you should keep in mind, the power dissipation in the standby mode is because of the standby leakage current. Okay. And also some of the leakage current may be present when the device is in the on state also. Okay. First one which we have is the PN junction reverse bias current. Okay. As we can see in the previous slide, this I1 component, this I1 reverse bias PN junction is present when the device is on and off. Now we can see this is a P substrate and this is a N-type drain and N-type source. Now this P and N plus forms a PN junction, and this P and N plus forms a PN junction. We can call it as a parasitic diodes. Okay, so this parasitic diodes are responsible for the current flowing, the reverse saturation current, which is responsible for the leakage power. As we can see, this is a CMOS structure. In CMOS, we have the PMOS and the NMOS. Okay. It is a combined or we can say the complementary MOS structure in which both type of MOS transistors, that is PMOS and NMOS, are fabricated together. Okay, so here P substrate will form a diode over here, and this P substrate will form a diode over here. Okay, this is your NMOS and this is your PMOS, which is created inside an N well. It also forms a diode, a diode, a diode within the PN structure, and all these parasitic diodes. Parasitic here means the unwanted diodes. The unwanted or the parasitic diodes which are formed because of the structure of the device, okay, is responsible for the reverse bias leakage current which flows, because as you bias the whole circuit, okay, so source of the MOS transistor is grounded, but we apply some positive voltage at the drain end, because of which this diodes become reverse bias, and in the reverse bias a leakage current flows through a PN junction diode, which is contributing in the leakage part of the device. Okay, next we can also say this leakage current is responsible because of the minority carriers flowing through the device. So also it is called as a minority current, and also electron hole pairs are generated in this type of connection. So which ultimately increases the depletion region and the reverse bias region, and the net current which is flowing because of all these parameters is called as a junction reverse bias current. Okay, here we have taken example of a NMOS transistor. So here we can see this N plus and P type substrate are forming a PN junction diode, and the reverse bias PN junction current flows through it. Okay. Now temperature dependence of again PN junction current is a leakage current. So we can say as the temperature rises, this current will also rise, that is the reverse saturation current, and ultimately the leakage power of the device will increase. Next comes the subthreshold leakage. Like I already told you, this subthreshold leakage will occur in the off state, that is when the gate to source voltage is less than the threshold voltage in the weak inverter region. Okay, because when VGS is equal to VTH, that becomes the strong inversion region. Okay, so when VGS is less than VTH, then this type of current will flow, and it is exponentially increasing as the VT is decreasing. Okay, because the much less the VT, more the subthreshold leakage, and also it increases exponentially with temperature. Okay, so we can see this is the MOS structure, and in this the subthreshold leakage current is flowing because the channel length is reduced. Because of that, VDD and VT have to be scaled down, and due to this reduction of the VT leads to the VGS. Less VGS has to be applied to on the device, and the weak inversion region is achieved at a much lower voltage, which because of which the charge carriers now gain sufficient energy, and easily some of them move from source to drain, and as a result this leakage current flows in the off state. Okay. Now this weak inversion current or the subthreshold current arises due to the inversion charges that exist at gate voltage below the threshold voltage, like I already told you. So complete surface channel is not formed, but some charge carriers gain energy and move from source to drain. Now next is the thin oxide gate tunneling current. Now this we can understand from the name itself, thin oxide, like we are reducing the channel length, on all other dimensions are also getting reduced as a proportional value. Similarly, oxide layer also has to be reduced. Now at when the oxide layer becomes very thin, there is a finite probability of carrier being passing through the gate oxide also. Okay, like we can see. So this type of current results in the tunneling current through gate oxide, and this type of current is observed in the devices which have a very less oxide thickness. Okay. Next is the gate direct tunneling leakage. Okay, so in short channel devices, basically these all are short channel effects. These all type of leakage dominate when the device length is reduced. Okay, so that's why we are again and again saying in short channel devices, the resultant of electric field of gate voltage and drain voltage causes electron to move in a zigzag manner. Okay, now because of this zigzag movement, some electrons gain extra energy even when the channel is not connected, and we can say the pinch off condition is there, and they try to move from the drain end to the either oxide layer or towards the surface, and we cannot predict the movement and we cannot predict the direction. It's just moving in the zigzag manner, so charge carriers may move here and there and get trapped either in the oxide layer or in the substrate, so it may move in any direction. So basically it is a gate direct tunneling leakage, that is from the via gate of the device the current is getting leaked away. Okay. Next we have the gate induced drain leakage. Okay. Now this gate induced drain leakage is basically when the gate, this is your gate region and it is overlapping. See, this is the overlapping in the source and the drain region. Okay, so when source is grounded and when we apply some positive voltage at the drain region, this GIDL or the tunneling based leakage current flows. Okay, because the application of strong and vertical and longitudinal feeds in this particular region. Okay, we have applied the VGS also, we have applied the positive drain voltage also. So this overlapping region experiences strong vertical and longitudinal fields. Because of that, this region may go into deep depletion region. Okay, so this region ultimately gets inverted. So because of that, some of the charge carrier sweeps inside the substrate. Okay, so we can see the direction of the current. So it is drain leakage because of the gate overlapping is there. So we give it a name, gate induced drain leakage. Okay. This junction tunneling current I already told you, which is because of the current flowing inside the substrate, because some of the charge carriers move in the zigzag manner or they gain a certain velocity, because of which their direction of movement cannot be controlled, and as a result they may move into the substrate and get trapped over there, which ultimately leads to the leakage current. Okay, next we have the drain induced barrier lowering. This type of current basically flows when the source and